And this must be good to the right side.
Okay, thank you. So like all the talks in this session, this is a joint work with the wonderful people from Aarhus University. So one of the main goals of Trillium is to prove termination of concurrent programs. So we'll explain how it works on this simple example. So if you start at the bottom in the entry point of the program, we allocate a new reference B, which contains a Boolean, and then we spawn two threads, yes and no, and each want to flip this bit k times. But the difficulty is that they don't want to flip it in any ways. So if you look at the yes thread using a compare and swap, it tries to flip it from true to false using a compare and swap. If it succeeds, which means that the Boolean was true, then it decrements its counter, otherwise it loops back. And no tries to do the opposite, or flipping from false to true. Now, does this program terminate? The answer is no. Because, of course, for one thread to make progress in any state, at any state, only one thread can make progress, depending on the value of B. So if B is true, yes can make progress, but no is stuck waiting for yes to make progress. So if the scheduler is kind of mean to us, and all these schedules no, then no progress will be made, and the program clearly doesn't terminate. Of course, in practice, it does terminate if you implemented this, because schedulers are what we call fair, which means that they kind of run all the threads that are able to run. So now the question becomes, does this program fairly terminate? And intuitively it does, because like I said, at each state, one of the two threads can make progress. And since the scheduler is fair, if the right thread runs, it will make progress, and if the other thread runs, it will not help, but it will not hurt either. So in the end, the progress is made and the program terminates. But how do we prove this kind of formally? So here, our approach is to have a program logic that can guarantee that a concurrent program fairly terminates. And there are already such logics. One prominent example is Tada Live. But there is no kind of free lunch in life, and while it has very strong guarantees, it's kind of less expressive than logics that only handle safety properties. For example, it does not have higher order go state, it doesn't have impredicative invariance, which means that you can nest invariants inside of each other, and so on. So in this work, we kind of try to take the other direction. We start from a logic which is very expressive, but can only handle safety, in that case Iris, of course. And then we try to see how we can prove fair termination of concurrent programs. Now there is a slight problem, which is that Iris kind of is based on step indexing, which kind of fundamentally says that it cannot only prove safety properties. And of course, termination is a liveness property. So we cannot kind of attack the problem head on, and we have to take kind of a roundabout roads. And I would like to note that this is not an artifact of Iris in particular, because the only way we know today how to have impredicative invariance is to use step indexing. So this is not just for Iris, but any logic such as Iris. So what we propose here is a logic called Trillium, and its purpose is to build a refinement between any program and any label transition system M that the user chooses. Now there are two reasons why someone would do this. The first one is that once you have this refinement between the model M and the program, you can transport properties from the model to the program. So here, in that case, it will be fair termination. And also, of course, it's well known that sometimes refinement is a very good way to specify in a very intentional way the behavior of a program in a way that kind of usual Hall triples cannot really handle. So if you go back to our program, we can use the model on the right. So here the state is a pair. On the first component, it's an integer, which corresponds to the value of the counter of the no thread. And the second component is a Boolean, which corresponds to the value of B in the program. And once you know the value of B and you know the value of M, you can basically recover the value of N, the counter of the yes thread. And as you can see, there are two types of transitions, yes and no, which correspond to the two threads. And here, in this work, we call them roles. And they're basically a kind of abstract threads that can allow us to talk about what does it mean for a trace of a model to be fair, because you need some kind of notion of thread. It is quite easy to see that it's fairly terminating, because basically at each state, one of the two transitions makes strict progress towards the left, and the other one just loops, right? And of course, this model is well-founded. And this is a sufficient condition for the fair termination of a model. And basically, this is kind of a more formal way of setting the argument that I made before about the program without having kind of many transitions that we don't really care about. Now, how do we prove this refinement? Basically, we use kind of standard iris proof methods. So we have an invariant which kind of looks like this morally. So we state that the current state of the model, which we can kind of talk about using this circle predicates, matches the kind of the physical state of the program. And then you just do your proof as you would expect. So this is kind of the first use to transport properties from the model to the program. And there is also another use, which is to specify programs. So here on the right, you have the, I think most of us know, the Tower of Hanoi game. So we have 3 stacks of disks, and we want to move them from the left one to the right one. And we want to keep the invariant that no large disk should rest on a smaller disk. And on the left, you have a program that I think many of us had to write when we were learning about recursion, which is a program that computes the solution to this problem. And the invariant, basically it does this by mutating 3 lists, L1, L2, L3, which corresponds to the disks on the 3 piles, stacks. Now, how can we formally specify this program? So clearly it's not sufficient to just specify what it computes, because in the end it just computes a swap of L1 and L3, which we can do atomically. And if we use Trillium, we can kind of prove the existence of a kind of what we call an intentional refinement, which guarantees that the program cannot skip any step, and has to do the exponential number of moves to reach the goal, which is not something that you can do with the usual ways of doing refinement in Iris. So far I've been a bit imprecise when I was talking about Trillium. So kind of as is usual in the Iris kind of body of work, Trillium is not itself a program logic, but it's more of a program logic framework, which is parametric in the programming language. And to use it, you have to instantiate it with a concrete program, with a syntax and the operational semantics, like we've seen just before. And now in case of Trillium, there is another thing you have to do, is that Trillium itself only guarantees lockstep simulation between the program and the model. And in practice, it's much too strong, because you want some kind of stuttering to be able to abstract things away from the program. And so here's up to the instantiation to kind of relax the notion of refinement to have something that is usable, but still useful. So in the paper, we have 2 instantiations. One is Ferris, which I've been kind of implicitly talking about up until now. So it's a new logic, and the goal is to prove fair termination of concurrent programs. Then there's another instantiation, which is Aneris, which is an existing logic, which was used to prove safety of distributed systems. And we kind of rebased it from the Iris program logic to Trillium program logic. And so now you can prove refinements of distributed systems. But in that case, the refinements are not fairness preserving. So in the remainder of this talk, I will only talk about Ferris. And basically, I will kind of give you a taste of how the instantiation of top of Trillium works, and how we kind of use Trillium to prove termination of concurrent programs. So if we start at the kind of the top, at the high level, the kind of basic recipe for using Ferris is that you have a program E, you want to prove that it's fairly terminating. So what you do is that first you find the model M, then using the logic you construct a refinement between E, your program, and this model M, and this basically amounts to proving some Hall triple. And then you prove that M is fairly terminating. Now of course the question is, to use this you have to guess a model M, and it has to be at the same time simple enough that you can prove fair termination, but close enough to the program that you can prove refinement, right? So there is still a lot of work. But on the other hand, it's kind of in a very useless way complete, because basically if you take for a given program E, if you take the model M to be E, the program itself, then all the steps are trivial in some ways. So like, now we'll explain kind of a high level how Ferris proves that a program is fairly terminating. So kind of, if you unfold the definition, it means that if a program is, if an execution is fair, tau prog, then it has to be finite. And since we've proved that the program refines the model, you can assume that there exists a model trace which is refined by the program trace. And now we'll see like what we need to know about which properties we need from the refinement to be able to prove this implication. And this works like this. So first, we have to know that this refinement preserves fairness, so that the model trace is also fair. Then we have, by assumption, the model is fairly terminating, so that the model trace is finite. And then we also need that the refinement only allows finite stutter, so that it preserves finiteness of traces. So then we can prove by this kind of detour that the trace is finite. Now before I conclude, I will kind of give you a taste of how this refinement relation is defined under the hood. So let's suppose we have a configuration C. So a configuration is all the threads as well as the global heap of the program. And we have some model state M, and we assume that they're related by this refinement. Now this is not enough information for us, so we have to assume a bit more knowledge. So here we keep track of a correspondence between threads and the roles, which are the labels of the model. Then each thread can have several roles, but each role has a single thread. And each role has a fuel, which is the natural number, so that it cannot decrease below 0. Now let's say thread 1 takes a step, and then it yields a configuration C prime. Now we can wonder which corresponding steps the model can take according to the refinement. So there are two cases. One is that the model does take a step. So in that case, it's row 3, which takes a step. And it has to be linked with the thread which took a step, right? So only, and then it can get a reward for taking a step. So it can kind of fill up its tank up to some maximum value, fuel max. And this is needed because of step indexing. But however, all the other roles which are related to the thread which took a step have to spend some fuel. And this way, if the thread 1 takes many steps, then all the roles have to take steps, otherwise the fuel will go below 0. And this allows to preserve fairness between the program execution and the model execution. Now there's another case. The model can just stutter, and in that case, to prevent infinite stuttering, basically all the roles have to lose fuel. And the way we define this relation formally is not to have a complicated refinement between the program and the model, but to have a very simple lockstep simulation between the program and a more complicated model, which we call fuel of M. So what happens is that when the user chooses a model M for Ferris, under the hood Ferris gives fuel of M to Trillium, which gives us then a lockstep simulation. So here I only talked about Ferris, but in the paper we have this other Aneris instantiation. And the main example is that we have an implementation of single degree Paxos, and we prove that it refines kind of an off-the-shelf TLA plus specification that we've translated by hand. And just, of the future work, I would just talk about the fact that, we're working on kind of merging the two and having liveness of distributed systems, and this Jonas doing this. And also, right now, while the logic is modular at the program side, it's not modular at the model side, which is a big limitation. And Igor is working on this. And I'm happy to take questions.
Question? Rabbit?
Thank you for the nice talk. There was already earlier work on developing an iris-based logic for fair termination preservation by my neighbor here, which funnily in a subsequent paper has also been called Ferris. But But could you maybe highlight the differences between that work and yours?
Yeah, so, well, one difference is that we had the chance of doing it after them, so we had the better iris.
Okay, okay.
So in particular, there's distinction between base logic and program logic and so on. And they had to change the model, I think.
But so what I recall is that the original Ferris was linear. Is yours linear or affine?
No, it's affine. So we didn't need to have linear resources, so we didn't have to change the model to.
What is the trick? How do you make sure that you don't need linear resources?
I think the intuition is basically there's a resource that you don't want to drop, right? In both cases. And here, basically, for each step, the weakest precondition asks you to give it, right? So if you drop it, you cannot take any step. So it's kind of threaded in the weakest precondition.
Okay. I probably should read the paper, or you should explain me offline. I don't immediately see it. But good to know that's affine. I like that.
We have a question online. It says, we are told that the limitation to safety properties is fundamental, but what about transfinite iris?
Excellent question. So in some sense, it's almost kind of orthogonal, right? And the fourth point in the future work is that we think that if we use Trillium on top of transfinite iris, the finiteness restrictions would lift. And the problem is transfinite iris that right now we don't know how to prove termination of concurrent programs, right? Because basically what they do in the paper is that they have a refinement between the program and just ordinals. But then you cannot talk about fairness or anything of ordinals. So I think it's, right now, as far as we know, it's orthogonal.
Okay. More questions?
So I guess these actually two. So the first is about in the paper, and you mentioned above, you have proofs of refinement of TLA specifications. The notion of refinement in TLA is trace inclusion, which is weaker than the notion of simulation that you have. Do you think there would be? Do you have any comments on that? Would it perhaps make sense to have a separation logic based approach based off a trace inclusion notion, or?
Well, I mean, first what we did, that we translated by hand, and then we had just a simulation with infinite unbounded stutter, which I assume is very close to trace inclusion. No?
Okay, well, and then the second question is that many of our compiler correctness proofs are based off similar refinement that simulation arguments. I don't think I saw here, but would be interested in the possibility of setting up the soundness theorem for something to a program logic against, say, like the referenced earlier paper, the ComCert semantics that combine these ideas with like setting up a simulation of the ComCert semantics. Did you think about that? Anything along those lines?
Not really. I mean, so this was the motivation of Joe's paper, right? They were looking at kind of one compiler pass. But yeah, I guess on the hand, it would be very nice to have a kind of a new program logic-based proof of ComCert. I think it's a lot of work as well. And I leave this for other people.
Okay. One last question while the next speaker sets up.
There's one online. The one online is, can you repeat how you defined fairness in the model?
So given a trace, right, you have a sequence of roles, which are the labels. And you want to say that if a role is enabled, whatever that means, then eventually it will take a step in the infinite trace. Or it's infinite, or it's finite, of course.
Let's thank the speaker again.